Hi, AB Calculus. You can see here we're doing 2005, question number 5, and this is the graph they provided. It appears that they didn't give us much else, but that's all we need. Alright, first we're going to start with part A. I'm using this so you can fast forward. If you don't need help with part A, you can go find the part that we're working on. Alright, so for part A, they want us to find the integral from 0 to 24 v of t dt. And let's go ahead and first talk about what this means before we even find it. Alright, remember, area underneath velocity gives the displacement. In other words, the net change in position. However, sometimes, not always, sometimes this equals this. What's the only difference between these two? This one will count all negative area. Absolute values makes it positive. But you'll notice here, this is velocity. Velocity is always positive. So if velocity is always positive, this doesn't have a job, and these are the same things. So, if these are the same things, yes, we could say this is the net change in position, but something even better we can say is it is total distance traveled. This doesn't always work. This is only true when your graph or your equation is positive the whole time. If the graph is always positive, then your net change in position is always your displacement. Okay, so how are we going to find this here? How are we going to find our total distance traveled? Well, this simply means find the area. So in order to find the area, I'm going to use one giant trapezoid. The area of this is one giant trapezoid, 1/2 the height, base 1 plus base 2. The height, just pick any height here, the height is 20. And then your base 1 and base 2. Your base 2 has this distance here of 24. And your base 1 is the distance from 4 to 16. That's a distance of 12. And this is an earn it question. You don't have to simplify it. But you would say this many meters is the total distance traveled, and you must talk about time, from time 0 to time 24. Alright. The only other thing, if you didn't want to make one giant trapezoid, that works, but you could have turned this into triangles and rectangles. So, if you did this, we have a triangle, 1/2 base times height. 1/2 base is 4, and the height of this triangle is 20. Here we have a rectangle. This rectangle is 12 times 20. And here we have a triangle, 1/2 base times height. 1/2 base is 8, and height is 20. And if you were to plug all that into your calculator, if you wanted to see, you get the same answer. So it's this many meters is the total distance traveled. So just another way of breaking up your area. Alright, that is the end of part A. And now we're going to do part B. Part B, find v prime 4 and v prime 20. Alright, v prime 4 simply means, okay, if this is the graph of v prime means find the slope of the tangent line at 4. Well, what is the slope of the tangent line there? Well, we have a slope over here. If you count rise over run, it's 20 over 4. And then we have a slope over here, which is 0. But at this one point, the slope does not exist. and they ask you to tell why or why not. And that's because there is a sharp turn. All right, let's look at the second one. The second one says, what is v prime 20? All right. Well, v prime 20 is the slope of the tangent line here at 20. So if we want to know that slope, we can just do rise over run. So notice it's a negative slope. And it goes down 20 and over 8. Now it does say indicate units of measure. By the way, of course, I could simplify this to 10 over 4 or 5 over 2. But they want the rate. Just kind of some things to remember. Our position in this problem is in meters. Its derivative velocity is in meters per second. So its derivative acceleration, every time you take a derivative with respect to time, you get another unit of time on the bottom. You're taking the derivative with respect to the derivative of time. That dt on the bottom gives another time h1. So the units are meters per second squared. And again, you can simplify this, but you don't need to. All right, that's part B. All right, let's go ahead and look at part C now. All right, part C asks you to make a piecewise function for acceleration. Now we already talked about the derivative of velocity being acceleration. So we just want to look at the derivative of velocity, or the slopes of velocity. You'll see how all the slopes are the same, and then all are the same, and then all are the same. So if we find the slope right here, the slope is rise 20, run 4. So your slope is 20 over 4, which I'm going to simplify to 5. That's what the acceleration is in this time frame. Here the slope is 0, so for this time frame the slope is 0. And then here we found the slope just a second ago. The slope we said was negative 20 over 8, which I'm going to simplify to negative 5 over 2. So my slopes were 5, followed by 0, followed by negative 5 over 2. Notice there's a sharp turn here and a sharp turn here. So when we're doing our slopes, we're going to say this was the slope when time was between 0 and 4. Notice there's not an equal sign at 4. At 4, there's no slopes, and there's no acceleration. That can be defined. All right, from time 4 to 16, our slope is 0, and from time 16 to 24, our slope was negative 5 over 2. And again, you just need to know that the derivative of velocity is acceleration, so we're looking at the slopes of the tangent line to finish this part. All right, that's it for part C. And now we're going to do part D. Okay. So part D says find the average rate of change. Now folks, there are two types of average. There is average value of a function, and then there is average rate of change. Okay? Average value of a function, average rate of change. This is what we want here. We do not want this. And in fact, they actually told us average value of a function is not on the AP exam. They're worried too many people didn't get to it. All right, so part D says find the average rate of change. Average rate of change is just average rate of change means slope, so average slope, meaning slope not through 1 point, slope of the tangent line, but slope through 2 points. And they want the average rate of change from 8 to 20. Now, of course, we're using velocity here. So it's v of 20 minus v of 8 over 20 minus 8. In other words, if you had velocity, they want the ordered pairs. All right, velocity is 8 comma what and 20 comma what, and you can look on the graph. It's at 8 comma 8. No, wow, bad Pike. 8 comma 20. Sorry, that's up here at 20. And now we're at 20 comma, and you might not know where this height is at. You can see the height at 20 is at 10. Now, how can I be sure it's at 10? Well, folks, my slope here is down 5 over 2. So it went down 5 over 2, down another 5 over 2. Or in other words, from 16 to 20, 16 to 24, the halfway point is 20. That's halfway. It's a straight line, so it's going to be halfway of the distance here. So if that's 20 and 0, halfway is 10. I travel halfway, I've used half the slope. Or whatever, that's not a proper way to say it. But anyways, so I'm going to take these ordered pairs and basically just find slope. So subtract the y's on top, and the x's on the bottom. I did something wrong. I flipped those around. Sorry about that. And I get negative 5 over 6. And take these two ordered pairs and look at these two ordered pairs. Does it make sense? I could have gone down 5 over 6. Well, down 5 over 6, down 5 over 6 again. All right. So that's the average rate of change. And then it says, does the mean value theorem guarantee? Well, the mean value theorem normally would look like this. I'm guaranteed f prime c equals f of b minus f of a over b minus a. It's a guarantee about the derivative. So here, if these are velocity, then we need its derivative, acceleration. So are we guaranteed that a prime c or a of c, are we guaranteed the acceleration at some point will be negative 5 over 6? Well, no, of course we're not guaranteed. Just look at what we had before. We already found acceleration. The acceleration was 5, and then 0, and then negative 5 over 2. The acceleration was never negative 5 over 6. So if it's never negative 5 over 6, why doesn't it work? The mean value theorem is not just some idea that works some of the times. It works all of the times if the conditions are met. Is the function continuous and differentiable? So as long as velocity is continuous and differentiable, the mean value theorem should work. But it's not differentiable. Velocity is not differentiable at time equals 16 because there is a sharp turn. So the final question says, does the mean value theorem guarantee? So the answer is no. The MVT does not guarantee because there is a sharp turn, or you could say not differentiable at time equals 16. And notice time equals 16. 16 is between these two. It is on the interval. So, sharp turn or not differentiable on the interval, mean value theorem doesn't work. And that's question 2005, number 5. Have a good day.